so now we will go to our topic. I will just try to explain solid state with the help of a PowerPoint. So just I'm going to now start the PowerPoint, and our topic today is solid state. So here is the PowerPoint. Here we will start the PowerPoint. Okay, we'll go for the full screen. We'll go for the full screen. So this is our topic. This is our topic for today's topic. This is our topic for today. Solid state. So you already know what is a matter. Matter is anything that is have mass and they occupy volume. And you already know that there are three states of matter which we call solid, liquid and gas. In addition to solid, liquid and gas, two now more states of matter has been added. One is called the plasma state, that is the fourth state of matter. And the fifth one is that is Bose-Einstein consolidated. So please participant, please switch off your microphones. Please switch off your microphones because otherwise it will be difficult to carry the class. Please switch off your microphone. Microphone bilak switch off kora. Etio dujon mane microphone on ase. So these are some three states of matter. We are not talking about the plasma state and the gaseous state. Again, I am requesting you, please switch off your microphone. One people, his microphone is already switched on. Please switch off your microphone. So these are the three states of matter. This is a solid state. This is a liquid. This is a gaseous. Now, what you can observe from this slide, that in solid, the interparticle space, so the solid is made up of particles, and these particles may be atoms, it may be molecules, or it may be ions. So in solid, the interparticle space, the space that exists between the particles, is very less. And in gas, the space between the particle is very high. And in case of liquid, the space between the particle is not less as solid, or it is not as high as gas. Which means solid, because there is no interparticle space, this interparticle space is very less. So solid is not compressible. Compressible means what? Compressible means the decreasing volume by applying pressure. So if you apply pressure upon a gas, then the molecules will come closer to each other, and as a result volume will decrease. Here in case of liquid, the interparticle space is intermediate. It is not less as solid nor as high as gas. So it gets compressible to very less extent. But in case of solid, you apply pressure, there will be no appreciable change in volume. Why? Because the interparticle space is very less. And as a result, what happens? This particle cannot move around freely. So solid are rigid in nature. So solid matter which compose rigidly having definite shape. So you already know what is a solid state. It is the state of matter which possess rigidity and they have got definite volume. Why they have got definite volume? Because their compressibility is very low, because interparticle space is very less. And they are highly ordered three-dimensional structures. So this one we will be discussing now. Now this solid, anything if you touch hard, if it got a definite shape, if it got a definite volume, we say it's as a solid. Now solid, there are two types. One is a crystalline solid and other one is a amorphous solid. So both crystalline solid and amorphous solid, they are made up of particles. And in case of crystalline solid, the particles follow a definite geometrical arrangement and which extends from one end to the other end. Which means In crystalline solid, the particles follow a geometrical arrangement which is long distance. Whereas in amorphous solid, the particles follow a definite pattern to only a short distance. In terms of physical property, crystalline solid, they have got a sharp melting point. For example, ice, it is a crystalline solid. And you know that melting point of ice is 0 degrees centigrade. But what about rubber? What about glass? Can you find its melting point in the dictionary? No, because glass or rubber, they do not have a fixed melting point. They melt at a definite range of temperature. So one difference between crystalline solid and amorphous solid is crystalline solid, the particles follow a definite geometrical arrangement which extend to a long distance, whereas in amorphous solid, the particles, they follow a definite geometrical arrangement only to a very short distance. Then crystalline solid, they have got a fixed melting point, whereas amorphous solid does not have a fixed melting point. For example, rubber, for example, glass. So amorphous solid, they are also called pseudo-solid. Pseudo means false. And they are also known as supercooled liquid. Why? Because amorphous solid does not have a fixed melting point. So they are regarded as supercooled liquid. So glass, rubber, plastic, these materials, though we call them as solid, but actually they are not pure solid. Only the crystalline solid are regarded as pure solid because crystalline solid has got fixed melting point. Amorphous solid does not have fixed melting point. So solid have resistance to change in both shape and volume. Solid can be crystalline or amorphous. Crystals are solid that consist of periodic array of atom, ion or molecule, and this arrangement is a long range order. That means the particles constituting crystalline solid, they follow a definite geometrical pattern which extends from one end of the crystal to the other end. Whereas for amorphous solid, the particles follow a definite geometrical arrangement only to a very short way. Is it clear? Now, solids can be classified depending upon the type of particles. If the type of particles in the solid are atoms, then they are called covalent solid. If the particles in the solid are ions, for example, sodium chloride, it is made up of sodium ion and chloride ion. They are called ionic solid. And if the solid is made up of molecules like that in ice, what you are having? In ice, we are having water molecules, and so they are called molecular solid. So please switch off your microphone. Otherwise, it will be difficult to carry the class. Please switch off your microphones. Let me find out who is switching, not switching off the microphone. Please switch off your microphones. Now, in case of solid, the particles are present there, and these particles, in between the particles, there is some force of attraction, and the force of attraction, it depends upon the type of particle. The force of attraction may be electrostatic force. Electrostatic force may be hydrogen bonding, or it may be an ion dipole interaction, or it may be a dipole-dipole interaction, or the force between them may be of covalent bond, for example in diamond. You know diamond? It is a allotrope of carbon. High secondary first year class you learned it, where each carbon atoms are covalently bonded to 4 other carbon atoms. So in between the particles there is a covalent bond. And in case of crystalline solid, where the particles are molecules, for example water, in case of or water or sucrose. So in case of ice, in ice the particles are water molecules and the water molecules are held together by hydrogen bond. So in case of solid, the interparticle force may be different. Correction. Okay, we lost the net connection, so again I will start it. So in case of crystalline solid, the particles are held together by different types of force, and the different types of force will depend upon the particles. And if the particles are ions, for example in sodium chloride or lithium fluoride, these are ionic compound, and the force between the particles is electrostatic attraction, that is the Coulomb's force. And in case the particles are atom, then the particles are held together by covalent bond, for example in a diamond. And if the particles of the solid are molecule, for example in ice, the molecules may be held together by hydrogen bond, or it may be held together by dipole-dipole force, or it may be held together by van der Waals force, etc. And in case of metallic crystal, the particles are held together by metallic bond. So these are the different intermolecular forces. So for example, to vaporize 1 mole of water, you need 41 kilojoule of energy to vaporize 1 mole of water. And whereas to break all the OH bond in 1 mole of water, you need 930 kilojoule of mole. So from this, what we find that intermolecular forces are much weaker than intramolecular forces. And the intermolecular forces, it measures boiling point. So if the intermolecular force is high, boiling point will be high. If the intermolecular force is high, melting point will be high. And if intermolecular force is high, the enthalpy of vaporization is high. And if intermolecular force is high, then enthalpy of fusion, it will be also high. So we can study the properties of an ionic crystal by studying the intermolecular force, because the physical properties of the ionic crystal will depend upon the intermolecular force. So this is hydrogen bonding. You all know how hydrogen bond occurs. It is an electrostatic attraction which takes place between hydrogen atom, and this hydrogen atom is linked with either oxygen, nitrogen, or fluorine. This is an electrostatic attraction like this. Then we have another electrostatic force. This is the hydrogen bonding in ice, in water molecules. So these are water molecules. This is one water molecule. This is one water molecule. So hydrogen of water molecule undergoes electrostatic attraction with oxygen of other water molecule, and this type of electrostatic attraction is called hydrogen bond. So this is the structure of ice. So this is the water molecule at the center of a tetrahedral, and the 4 water molecules are present at the 4 corners of a regular tetrahedral. And that is why there is a lot of open space between the water molecule, and as a result, density of water molecule is less compared to the density of pure water. Then we have another type of interaction that is called the ion dipole force. It is an electrostatic attraction between an ion and a dipole. So dipole, you can consider water to be a dipole because water is a polar molecule. One end of water carries negative charge, other end of water carries positive charge. So there may be electrostatic attraction between positively charged sodium ion and the negative end of the molecule, or from the negatively charged iodide ion and the positively charged end of the molecule. So this type of interaction is called ion dipole interaction. Then there may be also dipole-dipole interaction. So that is the electrostatic attraction between 2 dipole. So what is a dipole? It is a molecule with 2 opposite charges. One end is carrying negative charge, other end is carrying positive charge. So if you consider hydrogen fluoride, so in hydrogen fluoride, fluorine will carry partial negative charge, hydrogen will carry partial positive charge. So the negative charge of fluoride ion will attract the positive charge of hydrogen in other hydrogen molecule. So this type of electrostatic attraction, it is called dipole-dipole interaction. So then you can also have induced dipole interaction. Okay. Now you see these are the two structures of silicon dioxide and glass. So here silicon dioxide, you can see all the constituents, they have a definite geometrical pattern. It looks same in all direction. But in case of glass, as I already told you, glass is not a crystalline solid. It is an amorphous solid. And here you do not have a regular geometrical arrangement of the constituents. So in crystalline solid, the particles follow a definite geometrical arrangement from one end to the other end. But in amorphous solid, the geometrical arrangement does not follow regular pattern from one end to the other end. Is it clear? Now, a crystalline solid possesses rigid and long range order. In a crystalline solid, atoms, molecule or ion occupy specific positions. So amorphous solid does not possess a well-defined arrangement and long-range molecular order. Now what is a space lattice? Now you see that this is a structure of silicon dioxide. So here these are silicon atom, these red balls are silicon atom, and oxygen, and this greenish ball are oxygen atom. So red balls, these red balls, they represent silicon atom, and this white ball, they represent oxygen atom. And whereas in glass also it contains silicon and oxygen, but they do not follow a regular pattern. So you can draw the structure of silicon dioxide in the form of called a space lattice. So space lattice here, this is a space lattice, and the space lattice is drawn through points. Can you see these are dots? And each dot represent the particles in a crystalline solid. So what is a space lattice? It is an array. Array means arrangement of dots or points. And these dots and points, they represent the relative position of the particles in a crystalline solid. So here I have drawn a space lattice, and this space lattice contains various dots, and each dot represents atoms if the crystalline solid is made up of atom, and the dot will represent molecule if the crystalline solid is made up of molecule, and if the crystalline solid is made up of ion, then these dots will represent the ion. So this type of structure, which represent the position of the particles in a crystalline compound, it is called a space lattice. So space lattice, it is an array of points or dots, and these points or dots, they represent the particles present in a crystalline compound and their relative position. Now this is again a space lattice. Here you can see that this space lattice is made up of a repeating unit. Just imagine a brick wall. Just imagine a brick wall. I think all of you have seen the brick wall. So if you see a brick wall, you will find that the entire wall is made by repeating of bricks. So here also, this space lattice, it is made up of a small repeating unit. This repeating unit of a space lattice is called an unit cell. So here this is the space lattice and this is the unit cell. And this unit cell may be regarded as a brick. So one brick here, one brick here, one brick here. Then you get one line of brick. Then you place another line of brick over this first line. You will get another layer of bricks. and this way the entire brick wall is made up. So a unit cell, it is the smallest repeating unit of a space lattice. Now what is a space lattice? It is a diagrammatic representation of the atoms, ions or molecule which is present in a crystalline compound. So if you observe a space lattice, you will find that the space lattice is made up of a small repeating unit. This is one repeating unit, blue is, and this is the similar repeating unit just to the right hand side of this unit. And below also you find a similar repeating unit. So entire space lattice is made up of a repeating unit, and that repeating unit is called unit cell. And this unit cell, when repeated again and again, it makes the space lattice. Similar to the brick repeated again and again makes up a brick wall. So space lattice repeated again and again, it makes up a, what does it make? It makes up the space lattice. Is it clear? Clear, we say? Okay. Okay. Now, this is a particular unit cell, and unit cell can be classified on the basis of some parameter. These parameters are this angle, alpha, beta, gamma, and these are the edge length A, B, or C. So this is a particular unit cell, and here you can draw this three axes, and this is angle alpha, this is angle beta, this is angle gamma, and these are the edge length A, B, and C. Now in case of a cube, we already know in cube what happens. This angle is 90 degree, alpha is 90 degree, beta is 90 degree, and gamma is also 90 degree. And in case of cube, all the edges have same edge length. That means A is equal to B is equal to C. Then in case of a cuboid, alpha, beta, gamma are 90 degree, but A and B are equal and C is not equal to A or B. That means in a cuboid, two edges have same edge length and third edge have a different edge length. Now unit cell can be broadly classified into two types: primitive unit cell or center unit cell. This center unit cell is also known as non-primitive unit cell. So just now what I was discussing, that unit cell can be classified on the basis of the values of alpha, beta, and gamma, and A, B, C. So this is a simple cubic unit cell where alpha is equal to beta is equal to gamma. It is 90 degree. And all edges have same edge length, that A is equal to B is equal to C. Then these are the 7 different types of unit cell, and they are called as the 7 crystal system. So whatever may be the crystalline compound, the unit cell may be one of these 7 types. So these 7 unit cells they are called the 7 crystal system. Now, what is a primitive unit cell? In a primitive unit cell, the units occupy only the corners. The units are present only at the corners, and in non-primitive unit cell, units are present in the corners as well as in some other places. So this is a simple cubic unit cell. It represents the primitive unit cell, and in primitive unit cell, units are present only at the corners of the unit cell. So this is the cubic unit cell, and all the units are present only at the corner. And this is called a BCC unit cell. B stands for body, because you are having one unit at the center of the unit cell. That means this unit is at the body center, and other units are present at the corner. So this represents a BCC unit cell, which is a non-primitive unit cell. Then here you see this is another cubic unit cell. Units are at the corner: 1, 2, 3, 4, 5, 6, 7, 8. and you have one unit at the center of each face. This is one face. This is the top face. One unit is at the center of this face. One unit is at the center of the bottom face. One unit is at the center of the right face. One unit is at the center of the left face. One unit is at the center of the front face. One unit is at the center of the back face. So this type of unit cell, it is called a FCC unit cell, face centered cubic unit cell. This is the picture of a FCC unit cell. These are the units at the corner. 1, 2, 3, 4, 5, 6, 7. There will be 1, 8. And each face has a unit at its center. 1, 2. So in a cubic unit cell, there are 6 faces. So there will be 6 units at the center of 6 faces. And such type of unit cell are called face centered cubic unit cell. And this is another example of non-primitive unit cell. So this is a simple cubic unit cell. Units are only at the corner. This is a body-centered cubic unit cell. Units are at the center of a cubic unit cell as well as at the corner. And this is a FCC unit cell, that is a face-centered cubic unit cell, where units are at the corners of the cubic unit cell as well as at the center of the faces. So you have 6 faces in a cubic unit cell, 1, 2, 3, 4, 5, 6, and there are 6 units at the center of 6 faces. 1, 2, 3, 4, 5, 6. So these are the ball model. This is the BCC unit cell. These are the units at the corner, and this unit is at the center. And this is the FCC unit cell. These units are at the corner, 8 units. And this unit is at the center of the top face. This unit is at the center of the bottom face. This unit is at the center of the right face. This unit is at the center of the left face, etc. Now, these are the different types of unit cell. In cubic unit cell, there may be 3 types. That is a simple cubic unit cell, body-centered cubic unit cell, face-centered cubic unit cell. Then in tetragonal, there may be 2 types. Orthorhombic, there may be 1, 2, 3, 4. So the 7 type of unit cell will produce 4 different types of unit cell, which will include both primitive, these are primitive unit cell, and these are non-primitive unit cell. So this 7 type of unit, 7 crystal system, 7 unit cell type of unit cell will give a 14 different types of unit cell, which is called Breves lattice. So you can find it in your book, that is your Breves lattice. So these are the 3 types of cubic unit cell. So we will be only concerned with the cubic unit cell. Now this is interesting thing you see. So how many cubic unit cells are there? 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. So how many cubic unit cells are there? 8. Can you see it? 4 at the top, 1, 2, 3, 4, and 4 at the bottom, 1, 2, 3, 4. And this unit is at the corner. That means this unit is shared by 8 corners. Can you see it? This unit is at the center at this corner, and this corner is common corner to 1, 2, 3, 4, 5, 6, 7, 8. So each unit at the corner is shared by 8 unit cells. And what about a unit at the center of a face? This is a face. How many unit cells are there? 2 unit cell. And this unit is present at the center of a face, and this face is common to 2 unit cells. So from these pictures, what you see, that a unit at the corner is shared by 8 unit cells, and unit at the face is shared by 2 unit cells. Then what will be the number of unit cells which will be sharing one each? So simply remember, this is an edge, and you may put a unit cell here, you may put a unit cell here. So this edge will be common to 4 unit cell. So here you can see this is an edge. Can you see this is an edge? And this edge is common to this unit cell, this unit cell, this unit cell, and this unit cell. So each edge is shared by 4 unit cell. So a unit at the edge will be shared by 4 unit cell. So if a unit is at the center, if a unit is at the center of a unit cell, it only belongs to that particular unit cell. But if a unit is at the face and its face is shared by 2 unit cell, so if you put a unit at the face, it will be shared by 2 unit cell. So per unit cell, its share will be half. Can you understand? So again, I am showing this slide. So this unit is common to this unit cell as well as this unit cell. That means this unit is shared by this unit cell as well as this unit. So per unit cell, the share will be half. So half of this unit will be to this unit cell and half of this unit will be towards this unit cell. So any unit at the face, its contribution will be half. And if it is at the edge, and each edge is shared by 4 unit cell, so the contribution towards unit cell will be 1/4. And if this unit is present at a corner, so this unit is present at the corner, and this unit is shared by 1, 2, 3, 4, 5, 6, 7, 8 unit cell. So per unit cell, its contribution will be 1/8. Is it clear? So today we are actually running out of time because we have only 1 minute left. So tomorrow at the same time, we'll be having the second part of this class.